Welcome to video 2. We're on chapter 14, which is reaction rates. So today we're going to start relating these rates to actually rate laws where we can solve for how fast something's going, first reaction, okay? So again, working at the speed of life, I love that. Like your time while you want to react, like I said in video 1. Your fireworks, hey, we don't want those to react too fast because then they're right there on the ground. Nope, we want them to go up into the sky and then pop out. So anyway, how long it takes a diamond to form. Of course, people are trying to accelerate that. We make diamonds now, etc. Okay. So reaction rate, the rate is the change in the concentration of reactants or products over time. So what this is you're going to be asked, you can use R for reactants and P for products in all of these formulas. Now you're going to have a sheet in your reference books. I'm going to try to grab that in a little bit and show you. But anyway, average rate. So this is just like on average how fast it's going. It's not, and we have different types of rates we can take. We can take an instantaneous rate. Instantaneous rate, as you see down here, is at a particular instant. So at this exact moment. So t equals 0. So before it even starts, what's the rate? Probably 0. But we don't know, okay? Something could be already reacting from some previous thing or something like that, okay? The rate at a particular moment in time, obviously that can happen. So at t at, let's get the rate at 15 seconds or at 1 minute or whatever. Now things will react very differently. Of course, some could take 1 day, 20 days, whatever, okay? That is also done by measuring the slope of a curve that we graph when we talk about this, okay? So we're going to do this in our labs. We're going to be graphing the reactions that you guys are going to see, which are really, really cool. And then by measuring the slope, there's a lot in there, and you guys just heard the line y equals mx plus b. Sorry, that did not come to me very easily at that point, sorry. And we'll have a lot of information that we can get from that. So there is very useful information from graphing and using the slope in reaction rates. But I'm not going there yet. So when we react, okay, first of all, when we react, we have a lot of reactants, right? So what's going to happen is, all right, so as I was saying that, I was remembering I should go grab a worksheet to show you this. So this one looks more complicated, but it's not. So most reactions are going to have a curve, okay? It's not a straight line necessarily. Because what's happening as you start reacting, you have all your reactants. And so there's a lot more reacting. And remember we learned about concentration. As the concentration goes down, the reaction slows down. So it's a little less the next time, and a little less the next time it increases the rate. So we're slowing the progression gradually slows down as you approach the product, because now you have more product and less of the reactant. So you can measure that over here, okay? And of course, first on the reverse, that's the same idea. But here's what we got. When we are talking about reactants, in a reaction, we're losing them. So the rate of disappearance is what we call that, because reactants are being consumed. They're going away. We're using them, okay? And then the products is a positive change because we are letting them, hey, they're producing. They're appearing, okay? So what do we talk about the rate is all we have to do is take what's the change in the concentration of the rate over the concentration in time. Now we may use these independently and just say, okay, what's happening with the rate of the forward reaction with the reactants, or what's happening with the products, or we can relate them and find out all different kinds of things, okay? So change the rate with time, like I said, we're going to look at that steepness of the slope. You can tell a lot of things by that and the reaction rate. So here's how we relate concentration and rate laws. So this is a generic equation right here, okay? The rate, when we talk about this equation, first of all, these are our coefficients, okay? And then A, B, C, and D capital are our substances. Now, when we look at these, we have a rate value that we're going to get, a rate law, okay? So this is the rate law. And that rate law is always going to have this format. So this is generic, okay? But we're going to fill it in as we go with all of our different rate laws. So K is the rate constant. It is a K for constant. I know it doesn't start with a C, and that's a K, but that's okay. And it does change with temperature. So realize, yes, it's constant, but it's only constant at a temp, okay? So it does change as we go. So we already learned that, right? The temperature is going to affect it. The higher it goes, the more fast it's going to go, and the lower the temperature. Then we're going to take concentration of our reactants. Now the brackets are going to mean concentration. And concentration is the molarity most of the time, okay? Molality, that kind of stuff can be, but molarity is what we're going to be using here when we use the brackets. The M and the N, as it says right here, okay, let me go back, sorry. You notice we're only dealing with the concentration of the reactants only in a rate law, because that's all it depends on, okay? So we're looking at reactants only when we're talking about a rate law. Now, the values of M and N are reaction order. What order is this reaction going to take? Meaning, if I were to do something to concentration, let's say double it, and then I have a reaction order of 1, a first order reaction. That means that if I double the concentration, that will double my rate. They are just proportional, straight up. If I triple my reaction, and it's first order, it would triple. Okay, so you get the idea, right? Let me wait to go any further on this until I show you the notes so it'll make more sense. So again, it's for the reactants only. That's a big, big deal, the rate law. So whatever your reactants are, all you're going to use. And then the overall reaction order is very, very simple. All you're going to do is add up all the orders. So add all the orders of the individual reactants to get the reaction overall rate. Okay, reaction order. So whatever exponent is there. So in this reaction, since I don't have anything written here on the ammonia ion and the nitrite ion, they're both 1. So 1 and 1, they're both first order. So the reaction is first order in terms of the ammonium ion and the nitrite ion, but the overall is 2. So the overall reaction is second order. So we're going to use that later. All right. The larger the exponent, the greater the value. We're going to practice this on your Speedy Check 13 through 15, and we'll get there. Now, after we do a little bit more practice on this, and we'll bring it in, you're going to do those. They're going to practice again. If you had, let's say, whatever this is to the second, that means there's only one reactant, and that would be second order. The overall reaction would be second order. But of course, when you get more, let's just say reactant B has a fourth order reaction. Okay, that would be a fourth order reaction order and a sixth order overall. That doesn't happen very often. But anyway, now here's what I was talking about with the initial rates. Just real quickly to summarize it. If I can have a 0 order, that means it's not actually even in the law. So when I didn't have B in there, if I were to say, okay, I didn't even have that, that means B has no effect. It literally, I could double it, triple it, quadruple it, 20 times it. It doesn't matter. All right. First order, I've already explained, is directly proportional. So if you double, it doubles, triple, triple, quadruple, quadruple. Second order, if a concentration doubles, the rate will increase by a factor of 2. Okay, a factor of 4, quadruple, because it can't be 2 because that would be direct, So if you want to know the formula here, this is the reaction rate, how much it's going to increase is the value there. Now this number right here is how much I am changing the concentration. And this is the order. So if you notice, for my second order, I have a 2 on each of these examples. My concentration, though, I double it, that's the 2 there. I triple it, that's the 3. That's 3 times. If I were to triple this reaction, it's still second order, so it's just 3 squared, which is 9. So it's a 9-fold. So if we were doing a quadruple, so if I want to 4 times this second order reaction, I would put 4 for the concentration, square, because it's 2, second order, and 4 squared is 8. 4 times 4 is 16. Sorry, I can't do my math. 16 times will be the rate, okay? It'll go 16 times faster if I were to quadruple a second order reaction that was quadrupled in concentration. It follows with third hour. So again, third hour, that's what's coming next, is that this, again, is what we're doing, the concentration, so doubling, tripling, whatever. But notice now we have a third reaction order. So we're going to cube it. So 2 cubed, 2 times 2 times 2 is 8-fold. So it's going to take it up by 8-fold if it's a third order reaction. So it's like I said, as the order goes up, it affects it more. 3 cubed would do 27. Okay, so if it's quadrupled and we cubed it, 4 times 4 is 16. 16 times 4 is 64 times. Woo! All right. So again, the rate constant is affected by temperature, remember, and catalyst. It can make it go faster, but not concentration unless we once we've already established it. So if it's already second order or third order, we can't change that. Okay, so it does just depend on concentration. It doesn't depend on it's already there. All right, so anyway, that's the rate laws as they're written. You have to follow that. So those are what we'll be writing. But we're doing them without the experimental data. Later on, we're going to figure out how do we even get these. So today, I'm just going to be giving you these straight up with the numbers, the orders, and everything, and just interpreting that. Tomorrow, in the next video, we will actually be looking at the data and saying, okay, how does this work? How do I get those laws?